All right, so we've seen now this confidence interval. It gives us an interval that has a certain chance of covering the true mean mu. So, of course, we might like to make that interval as tight as possible. How can we achieve that, for example? So here it is. Let's look at the width of the confidence interval. Now, we said with a 95% confidence interval, that gives us the 1.96. Because remember, the 1.96 plus or minus 1.96 was for the standard normal. It's between minus and plus 1.96 95% of the time. So that's the linkage there. But let's look at the width of the interval. And so the width, it's x bar plus or minus, so the width would be just twice this. So twice that, and so there's the width of the interval. So we see that the width of the interval is a function of both sigma, which is the population standard deviation, and n. So n enters into the argument by taking the square root of n. So now, what if we want to be more confident? Instead of 95% confident, what if we want to be 99% confident? To be 99% confident, we have to pick up the 99.5% point of the standard normal, which is 2.58. And now what does that do to our confidence interval? The width now becomes 5.16. So it's almost a 25%, it's approximately a 25% increase in the width of our confidence interval if we want to go from 95% to more confident 99%. So as confidence increases, the width of the interval increases. But also note that as the sample size increases, the width decreases. So by making n larger, we're going to decrease the width. Here are 3 n's I just chose. So if we have an n of 10, so this is sigma over the square root of 10, which gives us a width of 1.24. Now, people say, okay, that might be a little bit too wide for me. I want to be a little bit tighter, please. I want to stay with 95%, and I want to be a little bit tighter. What can we do? Well, if we increase it to 100, then the width goes down to 0.39. And you get a little upset. Customer gets a little upset because they say, well, look, I'm choosing 10 times as large. My sample is 10 times as big. It's going to cost me 10 times as much. And all I've bought is, what is this about? Just a little bit over a third reduction in my width. And in fact, the problem is that goes down to the square root of n. We know that. And in fact, if you want look at this, if you want a 10-fold reduction, you're going to have to, 10 squared is 100, you're going to have a 100-fold increase in your sample size. All right? So it goes down as the square root of n. Now, the other thing is, of course, the smaller the sigma, the tighter are the bounds. So the bounds are a function of sigma. This is not something we can do anything about because our population has a variance or standard deviation of sigma. So this is what we've been saying all along. The more homogeneous our population, the more confident we're going to be in whatever inference we make. So we're stuck. We're stuck. This is what is a property of our population. Now, there are ways around this. For example, instead of talking population as a whole, if there's a difference between men and women, we might split things up and make some inference about the women, make some inference about the men. They might be more homogeneous within their groups, and then, in essence, what we do that when we do that, what we achieve is a smaller sigma, and thus a more homogeneous population by splitting it up into two. Might do something with kids, adults. Adults are much more homogeneous amongst themselves, kids. So that's the kind of thing we have to do. Short of that, we're stuck with sigma, and that determines the width of the confidence interval. What we can do is we can increase the sample size, but that goes up very, very slowly. It goes up as the square root of n. 1 over the square root of n is the speed at which this is getting closer and closer to 0, the width of the interval.